This world is full of uncertainties. Nothing can be said about future happenings with 100% surety. These uncertainties are usually found at individual levels. But when we study the average of a big mass of individuals, we find some certainty there. According to a law in statistics, which is known as law of large numbers, the average of the results obtained from a large number of trials is close to the expected value. In other words, the average of a large number of data is close to the population average. This average tends to become closer and closer to the expected value as more and more trials are performed, more and more data are added. This law is important because it guarantees a stable long-term result for the average of some random events. For example, in coin tossing, the law of large numbers stipulates that the probability of getting a hit will eventually be close to 0.5, 1 by 2, half. Hence, if the first 10 tosses produce only 3 hits, it seems that some unknown force somehow has decreased the probability. The law of large numbers requires no such mystical force. The probability of a hit may take long time to approach 0.5. Thus, according to the law of large numbers, uncertainty in the average performance of individuals becomes less and less as the number of individuals becomes more and more. It starts showing a deterministic phenomenon in a large system. A probabilistic phenomenon starts converting into a deterministic phenomenon as the number of observations starts increasing. Is it not getting an order in disorder? The law of large numbers is an extremely useful result with its powerful implications that is applied to a variety of disciplines, including probability, statistics, finance, physical sciences, etc. In the field of cryptography, there is a heavy reliance on probability when trying to decode messages encoded using some specific method. In English alphabet, there is a very specific frequency distribution for each individual letter. The law of large numbers implies that the longer the encoded message, the higher is the probability of the frequency distribution of each letter approaching the expected value. Similarly, if one wishes to know the probability that a specific word appears in a message or a piece of writing, the law of large numbers implies that this probability increases significantly as the length of messages becomes larger. Another fascinating law that is found in the nature of large data is what is known as central limit theorem. This theorem states that if we have a population from which we take sufficiently large random samples with replacement, then the distribution of the sample means will be approximately normal. The central limit theorem is important in statistics because it allows us to safely assume that the distribution of the mean will be normal in most of the cases. This means that we can take advantage of the statistical techniques that assume normal distributions. Normal distribution is the most important probability distribution because most of the continuous random variables in nature display a normal curve which is a symmetric bell shaped when values are graphed. What is really powerful and fascinating about the central limit theorem is that we do not need to know the probabilistic nature of our population in advance. We do not require knowing the probability distribution of the population. All we need to do is to collect sufficiently large samples that follow the criteria, and we can be sure that the distribution of the sample mean will follow normal distribution. In another way, we can say that the various populations that we study are different among themselves according to their probability distributions. They are not of the same probabilistic nature, but a sufficiently large sample drawn from any of such populations shows its mean having the same one distribution, and that is normal distribution. Is it not getting an order in disorder? The difference between the law of large numbers and the central limit theorem is that whereas law of large numbers assures us of getting the population mean as the sample mean, as the sample size tends to infinity, the central limit theorem assures us that the probabilistic law of the sample mean is normal as the sample size tends to infinity. The former gives the value of the sample mean, and the latter tells us the probability law according to which the values of sample mean vary. One is about the convergence of the value of sample mean, and the other one is about the convergence of the behavior of the sample mean. Both theorems exhibit stability in instability. Both exhibit certainty among uncertainties. Both exhibit order in disorder. Thank you.